Okay, welcome back to this last but not least session. It's my pleasure, our pleasure, to welcome Professor Marco Peccianti from Loughborough, Loughborough University, UK, obviously. Please.
Okay, just to make it clear, it was actually a highly sensitive university new option. One that was to change the spelling of our name. So, to complete it, yes, maybe yes. Okay, so, okay, yes, you're right. Nobody ever complained not to hear me well. Okay, thank you very much. So, we are going to talk about complexity in photonics. We have our specific cut because we are doing terahertz radiation. So I'm trying to show you how fundamentally we intersect the two things. And also in the while, try to show you what you're trying to do. We are building a new center. We are quite proud of that. And I take the chance to show it to you. Okay, let's see. It works. So where's Loughborough? Loughborough is very much one of the places much farther from the sea you can find in England. And it's the little dots there. And it's one of the largest companies in England. It's about 2.5 kilometers long. And if I have to tell you what was famous, of course it's famous for photonics now, but before our coming there, actually, if you consider in the medalist in the Olympian, you think about Loughborough as a nation, it would have been sixth or seventh. Okay. So we were one of the major universities in the world for sport education. We are medalists in swimming, basketball, whatever. It's that. You have to imagine that it's a big campus with a lot of stadiums, cricket fields, if you like, strange English sports. And of course, we receive a lot of awards, and because of this, there is a lot of course, other interest inside the campus that makes things running. In the UK, you have to think the university system is pretty much private in that sense. So, and this is our center. It's brand new. You can actually come and lift the pellicles from the screen if you want. You can find many of them. And it's a completely large infrastructure dedicated to ultrafast photonics, terrestrial waves, and integrated photonics altogether. We are about 24 people now with 4 faculties and roughly 5 major research lines, and they are almost entirely publicly funded. We do have industrial contract, but in this moment is research funded. So we have an endowment from university, but most of our research endowment come from grants. So those are the nice fellows there. It is winter. There is no tend to be cold around there. And we have basically a number of, okay, so among that we do, of course, sensing, integrated photonic circuits with a specific microchromes. It's our flavor of specialty. And of course, neuromorphic computing, because it's part of fundamentally our idea to create intelligent photonics like other people. Okay. So this is a presentation. Let me talk about the topic. So terraces used to be a quite niche, now it's very, very common. We identify with terrace with a strange no man land between microwave and infrared light. And the reason, if you basically try to identify standard technology associated with wavelength, you won't find none here, not public domain or publicly diffuse technologies. The reason because it was very difficult to do that. You are too fast for electronics. Your quantum edge too small for standard quantum mechanical processing. So normally the access was very difficult before the 90s. Probably you were working with electron laser if you actually ever touched first wave. Now things are changing. You can build optical benches. You can you have a lot of access. One probably the most important innovation was the access to femtosecond light, highly nonlinear optical processes. And there are now very, very cool applications. You can make biology. You can actually discover the signature of Goya underneath the canvas of a painting. terraces penetrating most common polymers and materials, and so it's molecularly active, which means that typical example, sugar and fructose and glucose, they have the same chemical composition, but they're just different orientation in space. Their terrace effect is completely unrelated, so you can separate them. So people have been using terrace for promoting sensing and essentially determination, but now there is a lot of quantum mechanical interest in order to probe quantum mechanical states, because the technology is a bit delayed. So the wave is a bit, about, say, 20 years or 25 years in late optics would. And terrace manipulation. So we would like to do the same thing we do in optics. With some perks, you want to do something that terrace can do. And there are some challenges. Let me explain you the first one, which is the chicken and the egg. So terrace is very, very good for sensing. But what you would like to sense is normally much smaller than a terrace wavelength, which creates a bit of a problem. So if you want to see something in this scale, you want to see cells, you want to see red blood, you want to see chromosomes, amino acid, whatever. But the beta's limit for the wavelength is there, which means technically speaking, you can't do imaging below that line. So people have been tinkering with near field approaches, like in optics did. And so what the problem is in terrace, however, is that you are interested to look much smaller than the wavelength. At the same time, you want the spectrum. You are not content of a monochromatic perception. You want the spectrum with the phase relation between them, because it's the normal thing people expect terrace to do. Terrace is very good for a reason. One of them is they can perceive a refractive index in absolute sense. I will show you. But I told you in a previous, many years ago, that in general optics, you don't measure refractive index. You use it in not, let's say, indirect way. Everybody in the, let's say, 3-4 people, I measure refractive index every day. And what I was trying to point out is that in optics, you convert refractive index in intensity. In terrace, you don't, because you have access to the electric field. So, however, if you want to look at subwavelength, and you want to know the spectrum of what you're looking for, the solution is having access to the field. If you have access to the field, you can do it. And there is a specific relation we need to study, but it doesn't matter. And this one created my RC problem. I was funded by the RC in order to create something called non-linear ghost imaging, which may ring Sandra ears. And in order to access to terrace, you access in a nonlinear fashion, and still applies consistency in principle to reconstruct image of something very, very small. And this is actually a terrace waveform. This is very typical. You can measure a terrace wave in field, not intensity, which is the most important difference to standard photonic applications. Okay, so what you do? You do an ultra-fast spectrometer. It's called in jargon time domain spectrometer. So you measure the spectrum in time, and you use essentially a pump and probe optical sampling, one of the pulse going to the object through a nonlinear device that creates the terrace. The other replica goes to a detection and overlap with the terrace, and if you're lucky, the optic sees the terrace, change some property, and you can measure what is changed as signature of the terrace there. You change the delay, and you reconstruct pulse. Because you have the field, the Fourier transform of the field is the spectrum in complex manner. So you have everything. Optical delay and attenuation in spectrum. So it's the most completed picture you can do of an object, because you have the depth and you have the absorption, the resonances. So very nice. This is the first image ever made in the terrace, not particularly defined one, but it's through the chip. So you pass into the chip, plastic is transparent. Okay, so, and this is actually the great beginning of this topic. Actually, I told you Alessandra Meringer here, she's looking at some of the literature. And what is ghost imaging? Ghost imaging is a way to reverse the problem of the imaging from the detection to the source, say in very poor manner. Okay, but at the beginning it was thought to be a completely quantum mechanical process, the historical image transcript quantum mechanics. Then it becomes a bit more classical, but then it's again quantum mechanics. Then it's something in the middle. And then eventually, who cares? We can actually do both ghost image using essential thermodynamical processes, correlations. It works anyway. And how it works? Works in this fashion. So if you sample an image, this is my daughter, and if you sample an image with a spatial sampling, so you illuminate the image with a pattern, and then you just extract the scattered light, some form on average on it, and you start to change the image, you can basically do correlations and reconstruct the image as the sum of the correlations you get. Basically, you have a big matrix, and you're basically, every time you sample the matrix with orthogonal function. This would be the best way, isn't it? And if you do that, this image forms. Now, this is in intensity. It's not in field, which changed quite a bit. But intensity works very nice. It's actually, the classical version is very much representing what people have been doing for single pixel imaging with classical sources. It's just the ghost imaging refer not to the construction of the image, but to the correlation you are using to construction of the image, which can be real, so you have to fill the correlated in space, or just correlated with the information you get, so an informatic version, IT version of it. Okay. So, how we do it on nonlinear ghost imaging? We did this for a number of years ago. What you do, you take sorry about it. It's actually, I'm losing control of this instrument. Okay, so you take an ultra-fast light, you shape the light with a spatial line modulator, you create patterns, you enter in a nonlinear material, and then from the nonlinear, you transmit to the object. And then if you want to increase the resolution, you place the object in proximity of the nonlinear material, so it is exposed to the near field of the machine. Why it is important? Because before terrace propagates, the granularity, the resolution of the pattern is actually fixed by optical diffraction limit, which is much better than the terrace diffraction limit, which is definitely fine. So if you want to exceed the wavelength resolution of alpha 200, you have to imprint your spatial correlation in the optical version of the sensing, not in the terrace one. Then you convert in proximity with terrace, and you get. And then you use a detection that, as before, is sensitive to time domain. It can do time domain resolution of the field. And if you do that, now I don't know exactly how to run this thing. And actually, we didn't test it, which is probably means it won't run. No, it is right. So you see, I was at the University of Sussex at that time. This, what you see, is practically 1 millimeter by 1 millimeter, and my wavelength in space 0.5 millimeter, which means the resolution is more or less 10 times better than the wavelength would actually suggest. Okay, and it is time resolved, which means each pixel should contain the spectrum. Which means if I have fructose and glucose and whatever, I should be able to recognize what those things are. There is a little problem in that we solved a year later. If you try to do that, you have the problem that space and time are entangled in there. Actually, in techniques, it's a very good word because it looks like exactly what happened in quantum mechanics. So the information is practically overlapped between space and temporal properties. So this is what you generally get. And you can reconstruct in a leaf. Leaf was the first image on terrace, so we try to do the same. It made sense. And in each point, you can see this one, for example, the spectral 1 terrace. You see the black because the leaf was actually fresh. So water is a terrace resonator. Then you left it dry, you look at the same leaf, and you find that the channel is empty. The vein of the leaf was empty. Okay, this is the phase image. I told you we have the complete spectrum, so phase is accessible at any wavelength and any frequency. And people, I would say we kind of create a generational thing about this problem. People have been trying to do what you're doing in different fashion, with different materials, different resolutions. And actually, there was even precursor publication based on mask that we are doing with a spatial line modulator, for people that are using mask even before. They've been using new materials, spintronic emission, they've been using organics, they've been using a lot of ways to try to imprint this pattern on the terrace wave. So the problem lies on the fact that when you launch a pattern in a subwave function, the green function, so the propagation of the relative time states propagation for field is extremely curved and warped in the space-time, which means you believe you launched a pattern. Actually, the pattern not only changed distribution, changed also time. The pattern arriving and landing on an object is not synchronized with what you thought what you were launching. This means that you believe that the pattern you were using in space-time is actually something else. This one, the first step of this problem is that if you have an object embedded in a subwavelength region, small, you are gonna reconstruct the spectrum, the space is gonna be wrong. Because if you start to warp the time and the space, your information, and you think you receive the information, but your information is not synchronized in time, which essentially means your spectrum is wrong. But the relation is actually quite possible. So what we did develop at the time, and is actually the main result of the RC project, is that we are in a way to go back to this phenomenon. So we can, if you want to readjust space-time information on something small, and because of this phenomenon, because the pattern you're using is basically changing in propagation, we were able also very recently to demonstrate that you can actually make three-dimensional imaging. So because each plane has a different pattern, I probably what I do is that if I multiply by a certain pattern, this means I'm looking at a certain plane. Okay. The only problem that in order to go very subwave, you need to emit a terrace in an extremely thin form. So the distance between the pattern you put in optics and the terrace generation must be so small in order to preserve the optical properties in the field. So I need to preserve the curvature must be the one induced by the optics. If you propagate too much, you start to lose your coherence, you start to lose potentially your near field ends, if you want. So in another completely different line, we start to investigate ways to generate terrace in extremely small, thin fashion. For example, surfaces. You can generate terrace from, I don't know, 25 nanometer material, which is quite small for the terrace. You can do it with, last time we discussed about quantum interference and dual. So you put two colors, femtosecond, you end up in a material that is very thin. And one of the reasons because the absorption to a second harmonic can be also 8 nanometer long. So you can have extremely narrow things. You can generate terrace. We also develop nanostructural surfaces. They can also generate terrace. Actually, we can generate terrace from silicon, which is tend to be very, very difficult because it is not a quadratic material. But if you think of the surface, and you make the surface nanostructural, what happens, you have a lot of aerodynamics on the surface. You can exploit those to generate terrace. Or you can simply do full technologically. You can take a surface, makes a lot of nice nonlinear resonators on top of it, that converts your light. Those are small structures, are under 50 at 1 nanometer tall, very small. And they actually enhance, you have your nice mode, and fundamentally you have much higher terrace generation than the standard surface. Or much more recently, we have been tinkering with spintronic emission. Spintronic is a nice technology. I don't have time to explain, but it's a ultra-fast magnetization non-reactive, and is extremely strong. So much that normally you can get to a few nanometers or 20 kilometers later, you can get the same nonlinear output of microscopic crystals. It's probably one of the strongest nonlinearity known. The magnetic are very strong. They're not very fast, so they are not very useful for optical wavelength. But terrace, they are very strong. Okay, and you can put on those samples that basically magnetic stack is a magnetic material between some metals. You can actually use nanoresonators to concentrate the light inside, to project the light inside the area you like. And basically, each time it's hit by a femtosecond pulse, you get a nice response there. So, thin material, we number of things. The last thing I show you, this is actually one of our patents. We developed an ink. It's physically an ink that can be painted on things, which is actually a quadratic material from metal. And actually, it retains nonlinear property even if it is disordered, which is impaired. It doesn't have to be ordered to work. And fundamentally, you paint whatever you want, a teapot, I think, and basically those are very different type of inks. So you can actually encode the details you want in the ink. You can make a variety less or more efficient, less or more shifted left and right, and whatever. Okay, so how do I interface? I use this thing to interface with nonlinear materials. Okay, fantastic. So that's okay. That's okay. One thing we had, we developed on a bunch of this thing, because the ghost image, the nonlinear version of it, sample space and time, we had this idea that we can use it to control complexity. One of the, in what way? So fundamentally speaking, one of the typical aspects of complexity in scattering, for example, is the time delay. In non-absorbing material, complexity is fully driven by a multi-path problem, which is fundamentally a multi-phase problem. And we had the idea, why don't we try to see if we can actually probe a complex device, a complex system, and maybe correct it, or maybe use it as a function, which is actually one of the most important recent developments. People have been trying to use scattering to create function you like, to remove the device and scattering becomes by device. So this is actually probably the precursor most important job has been done by Alarmovsk. What you do, you take a scattering material, you imagine scattering material to be a random combinatory system, and you say to yourself, okay, if it's a random, I can probably modulate my light in order to compensate for this random matrix. Okay, and from this modulation, I can get from the other part something I like. This is more a compensation thing. It's basically, I treat the scattering as a bad thing, and I try to make it work better. Try to pass from the other side, and actually works. They demonstrate they can get focus on the other side of a scattering. It's not particularly difficult in that sense. By the time it was absolutely, you can pass. Oh gosh, you can pass from a scattering. You can actually see to the scattering. A bit later, they say, okay, but if you want to have the temporal property, not the spatial, pass on the side. A typical problem in scattering is basically the break times sequence. So fundamentally, if you have an information that represented by time, a multi-path problem broke this time for you. So there is no longer a one-to-one relation between input and output. Which means whatever you're trying to do is based on time, you cannot pass through scattering. The scattering ruins your information content. But they did the same. And this is a bit more difficult because in a scattering material, you have a time-space relation. Because in a multipath system, every time you change the space, you also change the time of arrival. So if you do things smart, what they did, this is actually an autocorrelation, a cross-correlation. And fundamentally, if you want, is a wrong cross-space correlation. And demonstrate basically that in the non-optimized version, when you try to pass the material, there's no pulse on the other side. Practically, you can't see it. You do a bit of thinking, you change the space profile, not the so just the space. And also on the other side, you can form a pulse, which means all the harmonic, all the spectral components are synchronized from the other side. But this is only time. So, in doing this, what people usually do is that they observe the intensity of what happens from the other side. I stick my sensor on the other side, and I start to modify my input until I get something I like. When I'm satisfied, I stop. So if I want a pulse, I wait until the pulse, and I can create all gradient descent algorithm in order to fundamentally to converge to the solution I want if it does exist. But it's still based on intensity, which means what you're trying to do is optimize an intensity function you like with an intensity function that is actually going out from the material. It's just a bunch of energy distribution. Let's say you want to do something a bit better. You want really to have the field you want from the other side, not just the intensity, which looks like the field. One of the problems is that if you use intensity, you lack superposition principle. Intensity doesn't sum. On the other side, superposition is not valid for intensity, it's valid for field, but it's not valid for intensity. So if you launch the solution on one side and you transmit on the other side, it's not true that the sum of the solution would actually give you the sum of the effect. Because its intensity is not okay. It doesn't happen. So the solution is actually, if it is true, if I apply fields, but I need a system in which I can control the field, not the intensity. In optics, it's fairly difficult. You need a lot of effort to control actual fields inside pulses. But what I did is exactly this one. In Teres, we have the ability to control fields because we see fields. So what we did is that let's try to do this one. We basically print a pattern that we like in the optical side. Then we convert the optical side to the Teres side with a nonlinear phenomenon. Then we pass in a scattering medium. You have multi-path, multi-body system. Let's make an hole because I want the light actually to pass on the specific point, not everywhere else. And let's see what degree of control I can have on the waveform I get on the other side, which is not a pulse, it's actually a wave. Okay, I want to change the channel, I want to change the position, I want to change the flip, I want to flip the phase, pulse, yeah, done. I want to do all those stuff. Okay, this is the theory, which is fundamentally just a combinatory thing. You pass in a big matrix, just the matrix is valid for the field, is not valid for the intensity. And this is the experiment. So this is the simulation, this is the experiment. So what you can do, you start from a broken pulse. The scatter is not very kind with light. It breaks for the spectral coherence of the pulse. And but I can fix it. I can go back to the original pulse on the side. Oh, I can fix I can fix the opposite pulse. The one actually that is the same, but is actually pi shifted totally. And this is actually the experiment in which the red bad and broken thing is basically whatever you happen to be on the other side of our scatter. And the blue one is actually you start to think and you find out the solution and then you actually generate a pulse from the other side, which is nice. And also, this is a bit more complicated to address here, but you can demonstrate that this one means that you're actually transmitting more spectrum. Because you have interference, the field is not lost, you technically can increase the transmission on the side. You simply choose a solution that technically interfere more constructively on the side than on your back. And you can do a lot of things. So you can move a pulse. You can change the phase. Actually, this is not very good, but it's actually moved. But please note, I'm not changing anything. I'm not changing anything. This pulse is here, and this other pulse is 2 picoseconds forward and first. 2 picoseconds is huge. It's not moving anything. I'm just relying on spatial controls. So I want to go for the pulse. I don't need to change delays or something. I just change the pattern, and the pulse emerge from the other side in a different position. And then we saw this work, very nice, from Sylvain Gigam. And he says, if we can pass a pulse, we can pass an image, why don't we? So we can pass, we can create a peak on the other side. Why don't we try to make an image passing from the other side of the scatter? I have an image from this side, and I want to be able to project the same one on the other side. It's a kind of complex thing, you know. And they did actually this very fascinating setup in which they can measure the transmission function of scattering thing, which is absolutely a very, very difficult thing to do. But to do that, they need what is called ultra-fast spectral interferometry. Whoever ever built one, this is an extremely sophisticated and critical one because distances are extremely difficult to match. Yeah, they did it. They found out that you can actually pass a pulse, a Gaussian beam from the other side, and be able to reconstruct it. One of the problems, however, is that again, their merit function is the intensity. So they pulse the beam, but the phase is something that you can't decide fundamentally. We did the same. So we basically, what we did is say, okay, let's do something different. Let's make an image of what is passing from the other side of the image. We start to control the field, and what we did is that, you know what, let's see if I can make the terrace appears in different parts of the output. So I want the terrace here and with the right waveform. And this is the terrace X in this point. So this is the pixel, this is the frequency. So that frequency goes there. But I can make that frequency goes there and the other frequency goes somewhere else. Okay. So from this one, let's make an image passing. This is the vortex. This is just a simulation. This is a vortex in output. So in output from our sample. So the idea is that I want to represent something very complex. Phase and output. Vortices are quite nice in that. And the temporal pulse is a good one. So it is a vortex with a pulse. So what we did, this is the experiment. Sorry, again, I lost control. This experiment. Okay, there is a number of problems, and so we basically simplified a bit. But let's say we put an error, a little wire, on one side of our scattering, a very dense one. And the challenge was, let's see an error on the other side. And now, unfortunately, this projector is not very bright in that sense. Okay, but if you could see better, you will see that this is the image passing, especially in a certain time, is broken. You can't see anything. What you do before doing the image, you do the ghost imaging of your scatter. So, which technically one dimensional means you pass, you cover the object progressively, imagine it. So, basically, in the order to a lot of orthogonal function to exploit. Once you got this image, you don't need information. You put the hair here, you measure this image, you deconvolve, you get the wire. And there's absolutely nothing here that suggests there is actually an error. It's completely not intelligible, not in time and space. So, which basically we published very recently. So the point is that with terrace, you can see through scatter. In a much easier and better way, if you want, than normal incoherent light could do. Okay, I think I'm going to wrap up here. So the message I tried to convey, apart the fact that please come and visit us, okay, and is that the nonlinear ghost imaging is a way to control space-time. So we can probe space-time in systems in which space-time is relative. Wow. And using fields allow you to apply superposition principles inside, which means you can divide your problem into orthogonal functions and have access to the scattering method, which is what it forbids you to see from the other side. And using nonlinearity allow us to do this problem very, very easy to do, because in optics it's very, very easy to make a pattern. You can do it with a projector all the time. And then you convert it in terrace. Once you actually refine it, you get it nice. You put on terrace. So you apply linearity in this imaging mechanism. And you use it to see from the other side of things. Okay, and let me end with this one. No, this, and please come and visit us. Thank you.